Hello Info-Person, this is Anton, and I wanted to start this video with this picture. This is the iconic photograph of the first ever positron, and this is from 1932. And specifically, this is actually something that was captured in a cloud chamber and discovered by a physicist, Carl Anderson, who basically won the Nobel Prize for this. And intriguingly, this was only discovered a year after it was proposed and theoretically described, which, as you can imagine, back then was a huge achievement. But in this video, we're actually going to discuss a completely new milestone that once again kind of sounds like one of the plots from a science fiction movie. We're going to discuss what just happened in Switzerland not so long ago, because for the first time in history, scientists have now officially transported antimatter from one location to another inside a truck, with basically the picture to prove it. And yeah, they decided to call this Antimatter in Motion. And while a 4-kilometer drive around CERN campus might not seem like a long trip, or a particularly important achievement, for the world of particle physics this is huge. And so this Antimatter Express sort of marks the beginning of a completely new era in particle physics. And so let's discuss a little bit more about this, but before we start, let's briefly discuss antimatter just so that we're all on the same page. In other words, what exactly is this and why is this so important? And well, in the simplest terms, antimatter is a mirror image of regular matter. In other words, for every particle we're made out of, there's a kind of a partner or antiparticle that, though has exactly the same mass, has the opposite charge. For example, the partner to the negatively charged electron is visible right here. This is the positively charged positron. Similarly, for the positively charged proton, there is something referred to as antiproton, and it's negatively charged. But the most famous, and I guess the most dangerous property of antimatter is the fact that when combined with regular matter, it always annihilates and releases a tremendous amount of energy. Or just to rephrase this, these particles cancel out and instantly transform into a burst of energy, normally in the form of gamma rays and normally releasing a very specific amount of energy. And this fact makes antimatter incredibly difficult to handle and interact with. As a matter of fact, you cannot just store it in a jar somewhere, because as soon as it touches the sides of the jar, it's just going to annihilate and possibly even explode everything around it. And this brings us back to this recent achievement at CERN, the facility where a lot of antimatter is produced all the time. And to study antimatter, scientists at this antimatter factory had to come up with a new technique in order to see if they can transport it from one facility to another. Mostly because producing antimatter is very challenging, and so if scientists from a different lab want to study it, they almost always have to reserve time inside the CERN facility. And normally to study these particles, researchers use extremely powerful magnetic fields to trap these particles inside the vacuum. And that's the only way we can actually prevent these particles from touching anything. But even here, things are not that easy, mostly because all of the particle accelerators that produce the antimatter, and even the facility itself, is actually filled with a lot of different magnetic noise that interferes with a lot of delicate experiments. And so researchers here realize that if we can find a way to transport this antimatter to some kind of a remote location to study it there, it will actually make things a lot more interesting, and possibly even a lot cheaper. And so in this case, the team led by Christian Smora began what's known as the STEP project. This stands for Symmetry Tests and Experiments with Portable Antiprotons. And here they built a specialized 1-ton portable container referred to as cryogenic penning trap. This is a device that first uses liquid helium to keep everything super cold and powerful magnetic fields to keep everything in place. And that allows researchers to suspend any particle in complete vacuum. And in March of 2026, they finally tried it with antiparticles. And specifically here, the team loaded 92 antiprotons inside this device and then put it inside a truck, and basically drove it around for approximately 20 minutes. This is essentially what you're seeing right here. And to everyone's surprise, the particles returned safe and sound, without any of them disappearing or any of them being annihilated. Which essentially now proves that moving the universe's rarest and potentially most expensive matter to a slightly quieter place to study it is actually possible. And so eventually they hope to drive this antimatter to many different universities across Europe where it can now be studied directly outside of the facility itself. And once again, for particle physics, this is a huge achievement, mostly because transporting antimatter before was completely impossible. But this also matters for a lot of other reasons in particle physics and in other fields of theoretical physics as well. Mostly because a lot of modern cosmological models kind of rely on antimatter to try to answer some of the fundamental questions about the existence itself. In other words, if you're wondering why this is important, or why go to such extreme lengths and spend so much money to transport this, let's go through some of the reasons and some of the explanations. And first, just to confirm, this is the most expensive matter out there. 1 gram of this is approximately $1 trillion. But because it's so rare and because it's so difficult to produce, it naturally creates this fundamental mystery. Why is it so rare, and why don't we see a lot of antimatter stuff out there? Like, for example, antimatter stars or antimatter planets. And well, this actually leads us to the natural question of why does the universe exist the way it exists, and why is it mostly made out of particles, or regular particles, not antiparticles? And according to the current models of the Big Bang, the universe should have created equal amounts of matter and antimatter that would have annihilated right away. In other words, in theory, following the Big Bang, there should have been a lot of stuff that then annihilated and created a lot of energy, but no actual particles anywhere. But by looking around, we can tell that that seems to have not happened. So here some unknown factor allowed more matter to survive instead of being annihilated. And it's really that extra matter that then created everything around us, including you and me. And so here, by studying antimatter, scientists are trying to find this tiny flaw or tiny property, some kind of a broken symmetry as it's known, that might explain why matter seems to have won and antimatter seems to have lost. Now right now we don't have any exact answers, but in the last few years there's been some really exciting discoveries that did actually discover a few things about antimatter that we didn't know before. And that's because when it comes to antimatter, we've now entered what's known as the precision era. A lot of different types of studies have now started to narrow down the exact factors for this missing symmetry. Now first, there was an experiment a couple of years ago that we've discussed in one of the videos in the description that focused on gravity, and specifically trying to answer the question of, does gravity affect antimatter in the exactly same way, or is there some kind of a difference? So basically, does antimatter also fall, or does it basically fall up, being repelled by gravity, or maybe falls a little bit slower? And so here the AlphaG experiment at CERN confirmed that antimatter seems to fall exactly like regular matter, which basically ruled out anti-gravity ideas, but also suggested that in terms of properties, matter and antimatter seems to react to gravity in exactly the same way. Then, last year, there was a really intriguing discovery coming from the Large Hadron Collider. Here they observed a 2.5% difference in how some particles, in this case referred to as lambda beauty baryons, seem to decay compared to their antimatter counterparts. And this was one of the most exciting discoveries when it comes to this symmetry violation, specifically what's known as charge parity violation, because it basically shows us that some laws of physics treat matter and antimatter slightly differently. In other words, for some reason, the particles and antiparticles in this case seem to decay in a slightly different way, which was obviously kind of unexpected, but does show us that for some reason, matter seems to be just a little bit more resilient. Then, in 2024, the Aegis collaboration achieved the world's first cooling of positronium, an exotic atom made out of an electron and its antiparticle, which is of course a positron. And this was also an extremely important achievement, because positronium is usually extremely short-lived and annihilates in just a fraction of a microsecond. But by using a specialized laser system, and by reducing the temperature of positronium gas significantly, researchers were able to control positronium using these precise lasers, and thus control the annihilation for the first time in history. In other words, instead of just annihilating like electrons and positrons usually do, here scientists had just a little bit more control. And though right now we don't really know what to do with this yet, in theory this could lead to some of the first gamma-ray lasers, assuming researchers can figure out how to make this more effective. Then, extremely recently, we also had some discoveries from the project referred to as PUMA, Antiproton Unstable Matter Annihilation Experiment. And this is an experiment that tries to use antimatter in order to explore other mysteries. And so here, by using antiprotons, researchers can actually map the, skin of various radioactive nuclei. And specifically here, when antiproton is captured by a nucleus, it's usually annihilated on the very edge of the atom. And by measuring the ratio of various subatomic particles produced, scientists can determine if the nucleus has a neutron skin, which produces a lot of data crucial for understanding the mysterious neutron stars, or basically to test the equations of the state for neutron stars and a lot of other extreme matter in the universe. But more importantly, this directly links the experiments involving subatomic matter with some of the research involving astrophysics and a lot of these large-scale models involving neutron stars, pulsars, and magnetars. So basically now we have a way to study all of this right here on Earth. And all of this from just the last 2 years. And so when it comes to particle physics, technically we once again entered a new era. And while we're still kind of far from, I guess, fueling some kind of a starship using antimatter and using it to produce a lot of energy, which by the way would be extremely energy efficient, researchers are using antimatter to probe foundations of reality itself and to basically figure out some of the most extreme matter the universe has ever seen. And more importantly, it's no longer just theoretical or based on some kind of a model. These are physical experiments using actual antimatter particles. But the ability to transport antimatter from one lab to another, despite being symbolic, is actually a huge leap forward, allowing scientists to now study all of this in a lot of different locations on the planet. Which means that very soon, a lot of top-tier physics labs could have some kind of a system of antimatter on demand, which will hopefully allow more minds around the planet to focus on this and to basically help us answer the questions in regards to the existence of the universe, solving one mystery at a time. But at least for now, that's all we know. We'll definitely come back and discuss this more in some of the future videos. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.